Welcome back, Chemistry 30. This is the 1.3 section, electron configurations in the periodic table. So here we'll finally see how this can relate to the periodic table and really tell you how to do this quite easily. So use the periodic table to write condensed electron configurations, and also I guess we could say ground state electron configurations, and determine the number of unpaired electrons in an atom. So we just saw that the electron configurations of elements correspond to their locations in the periodic table somewhat. Thus, elements in the same column of the table have related outer shell valence electron configurations. And we'll see how that comes into play more with the next unit. As the table below right shows, for example, all the 2A elements end in an S2. So for example, beryllium, magnesium, calcium. So we have their corresponding noble gases that occur right before them. 2s2, 3s2, 4s2, 5s2. And as luck would have it, they're all in the group 2 area. So we could say NS2, where N is the main level, whether it's 1, 2, 3, or 4. And all 3A elements have an NS2 and an NP. So over here, boron, for example, 2s2, 2p1. Aluminum, neon configuration, 3s2, 3p1. Argon, we end up going through the 3d10 region, but 4s2, 4p1, etc. Now, I prefer that the order is the 4s2 before the 3d, because we saw earlier that the 4s region is actually below the 3d region. So there's more than one way you can state it, but I tend to go with the actual way with which one is lower. Let's see. As is shown in the figure on the bottom of the page, the periodic table can be divided into 4 blocks based on the filling of or order of orbitals. On the left are the 2 columns of elements. These columns, the group 1A, alkali metals, and the group 2A, alkaline earth metals, are those in which we have s orbitals being filled. These 2 columns make up the S block of the periodic table. On the right, we have our P blocks. So the S block and the P block represent the representative or main group elements. So what you may want to do on your pink periodic table, you could actually do this. So you could write down, so we have our periods 1 through 7. So even on the left-hand side, if you wish, you could write down, okay, where hydrogen is, lithium, etc. Right. This is the 1s, 1s row, 2s, 3s, 4s, 5s, 6s, 6s, 7s. And then, yeah, you see how they put the F blocks in here? Technically, this is below the periodic table. You could write the first block, which is the element La, as 4F, and then the element below it, which is AC, so the actinide series, that would be 5F. And then, so on your periodic table, this group is actually attached to here. So the first row here, which has scandium, 3D, 4D, 5D, 6D, and then your P groups, 2P, 3P, 4P, 5. So you can label that directly on your periodic table where the first columns are. So you could do that and you'll have that. So if you have that labeled, of course, and again, this piece here is actually down here is the F, and these 2, of course, are attached. So take a quick look at that, and you may wish to pause the video and just do that on your pink periodic table so that you have it. All right, so on the next page, there's a block in the figure that has 10 columns corresponding to transition metals. Yes, so yeah, this is what your periodic table looks like. So maybe we could look at this one. So you could type. So this is the 1s, 2s, 3s, 4s, 5s, 6s, etc. And then our F group is actually down here. So this is the 4F family, 5F family. This is the 3D, 4D, 5D, 6D. And then over here we have the 2P, 3P, 4P, 5P, 6P, 7P. There we go. So that's what this is just illustrating here, going down to the F block, and basically the order from starting at the top and going down, it corresponds to those elements. The number of columns in each block corresponds to the maximum number of electrons that each subshell can carry. Recall that 2, 6, 10, and 14 are the numbers of electrons that fill the S, P, D, and F sublevels. Because yes, we have one box, 2 electrons, 3 blocks, 6 electrons, 5 blocks, 10 electrons, 7 blocks times 2, 14. Thus, yes, so that's the S block has these 2 columns. The P block has these 6 columns here, which represent those electrons, etc., etc. And the D block, of course, has 10 electrons, and here we have 14. So using this, you can write the electron configuration of an element based solely on its position on the periodic table. So let's use the periodic table to write the electron configuration for selenium, which over here would be, let's see here, it would be right, let's see, I think it ends in, yeah, it's right here. So this would be where selenium is. If you look at your periodic table, you would see that. Okay, so the noble gas that occurs right before that here is argon. So that's where argon is. And of course, that's 1s2, 2s2, 2p6, 3s2, 3p6 is what argon is. Okay, so then from there we write down argon because that's where it is. And then we go from there. So we'll have to go over to here, the 4s region, the 3d region, and finally the 4p. So I think I have that outlined over here. Yes, take a look. So there's argon. And then, yes, I need to go to selenium. So it's an additional 2 electrons here, represented by 4s2, 3d10, 1, 2, 3, 4, 4p4. Notice that corresponds to this. Argon, 4s2, 3d10, and then 4p, 4p4. Look at that, how nifty that is. So yeah, this just outlines that, talking about potassium, etc. We fill up the 4s2 level. We then move into the 3d area, go up to 3d10. Finally, we move to the p block, whose principal quantum number is the same as the s block. So you'll notice that, yes, 4s, 4p, and the d will always be 1 less. So finally move there, counting the squares, move across the p block to Se tells us that we need 4p electrons. Therefore, the electron configuration is argon, 4s2, 3d10, 4p4. The configuration can also be written with subshells arranged in order. So yes, so you see here they put the 3d before the 4s, but I like to leave it how it actually is in terms of the levels. As a check, we add the number of electrons in the argon core, which is 18. So that's 18 electrons plus the additional ones, and we get 34, which just happens to be the atomic number of selenium. So we can do that as a check. Now it says here, what is the characteristic valence electron configuration of the 7As? So the halogens. Well, if you look here, they all end in, let's see, if this is the P region, that would be 1, 2, 3, 4, 5. They would all end in P5. They all end in whatever the main group is, N, P5. And of course, if we include the S block, the combined valence electron configuration format is, so yes, if I'm picking 4s2, 4p, well, it'd be over here, just one past selenium. So it'd be ns2, np5. So there we go. We could pick any row. 5s2, 4d10, 5p5. if we're excluding the D level. If we're just looking at the S and the P. All right, so we'll call it quits for that one, and we'll come back with part 2 and look at the remaining part.